We're Team Hydrate or Die-drate, and we're making a water bottle that tracks your water consumption throughout the day and helps you meet your goal. So to start off with, we made a PCB that everything runs off of. It's got the battery pack on the back, and then we plug into these different spots, a force sensor, buttons, and then the test and other things. So I'm going to talk a little bit about each component of our project. So for one, the sensors that we used a force sensor, a force-sensitive resistor, which will be in a circuit with a resistor that we had to choose. So I'm going to draw the circuit diagram for you. So this is the force-sensitive resistor. Let's call it R sub S. And this is a resistor that we get to choose the value of, which is on the PCB itself. And then we connect this. This will be V out. This is ground. We'll connect this to the MSP, and then we'll read this into the ADC. Okay. So the first challenge that we had to face was calculating this R1 value. We did this to find a reasonable value. We looked for a voltage divider. So V out will equal R1 over RS plus R1 VCC. So from this, we looked for values that would match comparably about to RS to have the greatest swing. We ended up choosing 100K, 100 kilo ohms, because it gave us the best swing with the voltages that we had. And also, we had a service mount resistor that had that value that we found in the 241 lab. So that's what we did. So then that means as the resistance of this increases, the V out should decrease. However, we have a graph for pounds versus ohms. The more pounds you put, the more force you put on it, the smaller the resistance. And it starts out extremely steep and almost logarithmically, and it starts to flatten out more into a linear region. So we operated mostly in this linear region from, how many pounds, Sachin? Like, at the smallest, half a pound? Mm-hmm. Half a pound to about 3 pounds, which was inside of that linear region. So that's the force-sensitive resistor. Next up, we use the A to D converter, which we use to read the V out value. This was calibrated to use a reference voltage of 3.5 volts, so VCC, so that we could have a full swing from VCC to ground. And our ranges for V out that we read were actually about 2.7 to 2, 2.7 to 2, which is pretty good. So we sort of stayed in the middle of that range, which was pretty nice. One of the problems that we faced with this was actually calculating the values and the ranges that the ADC produced corresponding to the voltage out. So the way that we found that, I'll erase this and write that formula out. So the ADC is going to be a 10-bit analog to digital converter. So that's 1024 possible numbers. That's over a range from 0 to 3.5 volts. So you're going to divide this, so 3.5 possible volts divided by 1024 sort of bins or numbers to put it inside of. Gave you the value that we were looking for, which ends up being about 0.0034. Or 35, I think it was, 0.0035. Which you then would take whatever voltage value you want, divide it by that, and that'll give you the number for the ADC. Or vice versa, if you have the ADC value, you can multiply it by that, and that'll give you the voltage that you should be expecting at V out. So next up, we used SPI to communicate with the LEDs. So we had a string of LEDs, 8 LEDs, that we used to communicate different information to the user of our product. We had a lot of different displays. You'll see that when we demoed the product, but we used SPI to communicate with it. It was the easiest. We wrote a whole bunch of helper functions that made it all a lot easier. So the biggest part of this was when the device was in use. So first I want to talk a little bit about the state functions that we wrote. So we had sort of like an initialization state. and then that went into a use state. And then once the goal was reached, that went into a, what we called the goal state, or an end state. So whenever you turn the device on, it goes into an initialization state. Here you have to let your water bottle calibrate for however long it takes. So what we do is we wait for about 5 consecutive ADC, within a threshold, 5 consecutive ADC values. So we used sort of like a debouncing, right? Debouncing of the ADC values. Just to make sure that they were consistent, because they fluctuated quite a bit. So the initialization did that to get the initial water bottle weight, and then we would check to see or ask the user for what their goal for cups of water was. You did that by pressing a button and filling up a meter. So you could have from 1 cup to 16 cups a day as your goal. And none of this was done in low power. After that, it goes into a use state where it shuts down completely into low power mode. Every about 4 to 5 seconds, it pops on from the watchdog timer. So the watchdog timer wakes up. The watchdog timer wakes it up. Which prompts the ADC. Which we then check and debounce. If that value is stable, we update our current weight. And compare it to our previous weight. Then that weight change is what we use to calculate the ounces from the weight. Furthermore, we use buttons inside of this low power mode to check to see what your progress was towards the goal. So let's say you had drank 3 of the 8 cups that you wanted to for the day. It would pop up with 5 LEDs displayed to show that you had 5 cups left. So the only other way out of the use state is to reach your goal. And once you reach your goal, it displays a goal animation, which looks very pretty. And then it goes into the goal state, where it once again goes into low power mode. And that low power mode, whenever you press a button, will show you the goal state, the goal animation, so that you know that you've reached your goal. You don't have anything left for the day. And then waits for the user to turn the device off and turn the device back on again in order to reach the initialization state once again. Now we will show you a demo of the product.
This is the intro sequence when it's turning on. That is the calibration sequence. And then so each LED represents 8 ounces of water. Right now it's preset to have 8 ounces of water as your daily goal, but you can change that daily goal by increasing up to 9 glasses of 8 ounces of water, or 10 glasses, 11 glasses, or you can go down. For the sake of the video, we are gonna do 2 glasses as our goal, and then when I click both buttons, it's gonna indicate that it's ready to go. And then you can check your progress by clicking a button. I'm gonna drink 8 ounces of water, and then it's gonna check. The LED will show the progress after it figures out where you're at. Means you're at 1 glass now. Now I'll drink another glass of 8 ounces. And then we'll see where we're at. And then it should show you a finishing sequence to congratulate you for meeting your daily goal. It should be checking. And there's the congratulations sequence. Thanks.